PhD proposal.
We're going to get rolling. Hello, everyone. Welcome to the second seminar of the semester, correct? Yes? As a quick heads up, there is a post-seminar reception next door. This is not like the big giant dinner and beer thing that used to be in the past. The idea behind this is to have more of a conversation, get a chance to continue the discussion. There'll be some light refreshments, and it's mostly designed to kind of continue this conversation, and that will happen after everything is done here. Hello, Howie, for taking pictures of us.
You never know when that'll be handy.
I know. Lesson number 1, black milk comes. Okay. So what I wanted to do, though, is most of you who have ever seen me do this, I use very short introductions because as a speaker, I hate losing time. So all I'm going to tell you about Hadas is she does really cool work and has lots of projects in a lot of different areas. So enjoy.
Yeah. Okay. Thanks, Aaron. Thank you so much for inviting me. I'm very. Do we clap? Clap. Very excited about being here. So I figured when I was making this talk, it's good to kind of articulate to yourself what is the purpose of the talk, right? So what am I trying to convey? This is not a class that I'm teaching, which needs to teach, I don't know, common filter, but rather I'm trying to give you a taste of the things that I do. So I'm going to give you a big overview of what I'm interested in general. I'm going to give you very quick examples that fit within that vision. And then I'm going to spend slightly more time on 2 projects that, again, fit that vision, but to give you a little more technical details. So that's kind of roughly the idea. It might be the case that the second part, I will be running out of time, so I'm just going to skip it. I'm not one of the ones that I have to go through all my slides. In addition, anytime you have questions, please stop and ask me questions, because that is more fun. So before then, I figured I'd totally put a plug in for robotics at Cornell. Robotics at Cornell spans multiple colleges, two campuses, multiple departments, and we're always looking for students, and we're also, every year we have faculty hires. So this year, computer science and electrical engineering are hiring in robotics, and both at Cornell Ithaca and Cornell Tech. So happy to chat about that as well. If there are any undergraduates here, postdocs, and so on. Okay, so this is a RI seminar. I would be remiss if I probably should not have volume there. I'd be remiss if I didn't put any robot videos. So you'll see I'm putting robot videos of companies. Just kind of give, not that this audience need any introduction to state of the art, but kind of the things that I find really exciting going on. So we have mechanisms that are amazing. I love that video. I know there's a newer one, but I still really like that one. A lot of advances in perception and figuring out where things are, and so on. Advances in HRI, so fielded robots in the HRI domain, in this case a hotel. Whether it's good fielding or not fielding, we can have a discussion about that later, but for now. But we can kind of see all these advances, right? But ultimately, how do these things happen? How do we create these systems that have these amazing physical capabilities, perception, HRI? I would argue that this is the typical design cycle. This is typically the way we do robotics. Okay, robotics as a system, if you will. So we have some informal specification. I want a robot that puts on lipstick. I have a designer, an engineer, an amazing, in this case, an amazing, as she calls herself, non-engineer, but really she is, that builds the system. And then you create the design. So the person creates the design, or the team of people, which is much more appropriate, creates the design. And then there's a process of testing. So I'm going to try it out. It's going to work not well. I'm going to try it out again. And that's kind of the design cycle. That's kind of the way we develop systems these days. So what I'm interested in, and what my group is interested in, is taking that, changing the paradigm a little bit, changing having the designer with the expertise create the system, do the testing, but rather think about how to automatically go from specifications, from a description of what the system should do, make a robot that puts on lipstick. So transforming those specifications into guaranteed behavior or structure or control when we can, and feedback when we can't. So why can I not do this? What is the problem that's preventing the system from doing that? So I'm going to call this formal synthesis for robotics. I'm putting formal in quotations because people use the word formal synthesis, especially in kind of the controls community, the hybrid system, formal methods, but we don't really have a good definition for what that is. And a while ago, I went to a doctoral seminar where we tried to define that, but we couldn't. So we kind of know what it is. So if you have any questions or disagreements, we can talk about that. So what does this mean? This means that the top one is kind of where we kind of are right now. And of course, I'm exaggerating. Of course, there are people who are doing automation. There are people here who are doing these things in a really, really great way. But the way I want, the shift is going to go from, instead of having this informal specifications, I have these abstractions, these pieces, these building blocks, whatever that means. I have specifications, which tells me what I want the system to do, what I want the robot to do, and so on. I'm going to run it through some, I'm not going to call it a black box because it's never going to be really a black box, but I'm going to run it through some automated process that automatically generates the design. So now what I can do, I can go from an expert designer to my lovely high school student, specifically my daughter, who is very smart but not an expert. And what she could do now is provide mainly the specifications. Maybe the user would provide some of the abstractions, maybe they would change it, maybe the abstractions will come from a designer, for someone who's an expert, and create the abstractions and specifications. And the second part, which is very important, which is kind of the thing that we get from the testing, from the intuition of the designer, from the knowledge that they have, is getting this feedback. And this feedback can be things did not work well because. It might work better if you had this. And that feedback can go in multiple different layers. It can go back to the user, basically say, I can't do this because, ask me to do something else. It could be used to automatically change the specification, change what we want the system to do. So maybe I can't, pick up this, pick up the laundry and move it into the other room, but maybe I can push it, right? Maybe there's other specifications we can do. And maybe I could use that feedback to refine my abstractions. So kind of the transparency talks about how difficult it is to automate these things. So to provide information is easier than to change the specification automatically, which is still possibly easier than changing the abstraction. That was weird. Okay, so what I want to do now is I want to give you a very whirlwind view through 3 projects that we've had, where we talk about, what I'd like to try to do is illustrate what I mean by abstractions, what I mean by specifications, what I mean by the algorithm, and what is the design and the feedback. So this can go from mechanical. So for example, lovely heavy robotics modules that we have in the lab and we like very much. That will be my abstraction. Those are the pieces I can put together. My task might be reach points in space while avoiding obstacles. What we did in this paper specifically, we used program synthesis. Turns out it's probably not the best way to do it, so we were kind of looking at other things. But ultimately, what we get is a design. And there's some really cool work here, Julian and Howie, that kind of treated the same problem, but from a different perspective. So it's really, really nice stuff. So we created a structure and the control that will guarantee that the points are reached while the manipulator avoids obstacles. But if we can't, what we can do with the encoding that we have there is provide feedback in the following form. I can either say, I can find you a manipulator, but it can only reach some of the points, and here are the points I can reach. Or I can provide feedback in the way of saying, oh, you know what, I can't do this with one design, but here are 2 designs that together will solve your problem. So that's one form of feedback. Another example that we had was this is in collaboration with Mark Kim at Penn and Mark Campbell at Cornell. So these are S'mores EP. These are modular robots. They connect using electropermanent magnets, so they can be turned on and off. So what happens here is I can control not only the motion in space, but also the configuration. What is connected to what? And I can do this in I can self-reconfigure because of this magnetic connection that I can turn on and off. And now my space of abstractions is actually going to be a library that includes configurations and gates. So what is the structure, and what are the motions that are related to those structures? So for each structure, I can have multiple gates, multiple motions associated with that. Then we can label these motions, or these types of behaviors, with different properties. So maybe climbing is one. Pushing could be another one. Moving straight or turning would be another one. And in this work, we basically created the library. We labeled them by hand, the different properties. But this can definitely be automated using machine learning, which is, I mean, I had undergrad kind of working a little bit, but we just never published it. So I have that abstraction. We also have sensors. So now we have information from the environment. And here we're abstracting the sensor information into kind of types of environments. So maybe I have stairs, maybe I have a ledge, maybe I have just movable space. And then what we'd have a specification. In this case, it's in linear temporal logic. We'll get to that. Which I can write specifications such as, if you see stairs, always, when you see stairs, you need a configuration that can climb. So I'm planning, or I'm writing my specifications over the properties in my library. So there might be multiple, typically there are multiple configurations and gates that satisfy this property. So now this is my specifications. If I see stairs, I have to use a climbing configuration gate with climbing abilities. If I see pink, I want to pick up an object. That is kind of a requirement. Things in blue are sensor information. Things in black are properties over the actions. So in this case, we use reactive synthesis, which I'll talk a little bit about in a bit. And the type of feedback we can get is we can say, I'm going to synthesize, but then based on the specification that I write, it might turn out that I need a configuration gate that needs to both climb and pick up an object at the same time. Right? If I see stairs and a pink object at the same time, I need a configuration and gate that can do both. And what I can do is a priori figure out that I actually don't have the right configurations gate for that. So a priori, I can say, you know what? I might not be able to do this task because what happens if I see stairs and a pink object at the same time? So that's kind of the type of feedback we can provide. We can also provide other types of feedback coming from the logic. So if there are any contradictions, if there are any things that are inconsistent, there's a bunch of things we can provide feedback about. But here we can also provide feedback about missing configurations gates to do this task. Okay, so here's like every time I give a talk, this is kind of the point in which I say the following disclaimer. So synthesis, right? The synthesis, the idea is automating from specifications to system, whatever, controls, structure, both, and so on. If you have a given system and you wanted to do a specific task again and again and again, and you don't need to change that task, synthesis is not the right way to do it. Synthesis allows you the generality of being able to adjust your task, adjust your behavior, but a specific solution for a specific problem will be optimized for that problem, and that's what you should do, right? So if you're trying to build a robot that will always, I don't know, if you want to build a drone, right? Don't use synthesis to build a drone, just build a drone, right? Maybe that was a bad example. But in any case, that is kind of where I'm going with this. And the reason I'm saying it now is because I'm going to show you, actually let me show you this. Here's kind of where I'm hoping to show you the power of synthesis. Because here, what you'll see is the modular robot starting from the same configuration, given the exact same task. The task is look for a pink object and go and drop something there. So it has something connected to it magnetically. We go, I mean, there's no grasping or anything, but we're going to go and we're going to turn off the magnet, it's going to fall. The exact same specification, exact same initial condition, so initial configurations, exact same abstractions, so configurations and gates I can choose from. And the behavior is going to be very, very different because the environment in which it's working is different. So you will see different configurations, different reconfigurations to different behaviors. So again, let me run this. See if they're both running. Yeah. All right, so they see on your left, the pink is at the top of the stairs. So it needs to reconfigure into something that can climb stairs. This configuration cannot. So it's going to dump a bunch of the modules. It's going to dump a bunch of the modules, and then it's going to climb up and drop the thing, come back, reattach. On the right-hand side, it sees it's kind of, the pink is kind of on top, so it's reconfiguring into this kind of proboscis, and please note it's definitely sped up. And what it's going to do, it's going to go and kind of put something on top. Right? Exact same task, exact same library or abstraction, different behaviors because of the environment. And this is fully autonomous, based on sensor information only, no hacking, no, and so on. The way we're doing reconfiguration, you can see the April tags on the modules. There's a webcam pointing down that can see them, and they're doing the reconfiguration based on that. So again, that is, again, fully autonomous. So the first example was purely mechanical, or mechanical and controls. Here we have the notion of extra configurations, deciding on the shape and control. Is it still running? Let me not distract you too much. We've also looked at having, a robot. Baxter, question?
Sorry, so does abstraction refer to a library of motion primitives?
In this case, abstraction is in general, the way I would think about abstractions is a way to capture your physical world with a finite set of something. All right, it's something that I can compose together. In this case, my abstraction, I had two abstractions. I had abstractions for the sensors, so the environment. So we had a few kind of types of environment. And for the motion and action, we had a library of configurations and gates. That was the abstraction here, yes. Okay, and in this case, in this case, my robot is a Baxter that has different skills. My specification is in natural language, so this is together with Tom Howard, who's at Rochester. And now we mapped the natural language to LTL. The grounding is also done through learning. And then what we can do is we can compose different Baxter actions to be able to create the specification. So pick up the blue blocks, drop it on your right, pick up the red blocks, and drop it on your left. So this is the example. This is what happens, right? So this is what happens when we run this. So we synthesize a control, we run this, and it's doing the correct behavior. So we synthesize the correct system. Now it might not do what you expect it to do, right? It picked up the blue, and it's just hanging there. Now it's going to pick up the red, it's just going to hang there. This is perfectly correct behavior. There's nothing, this is exactly following my specification. But it is a bit weird, right? Why is it standing there with its arm extended and not just dropping the blue block and coming back? So this is an artifact of synthesis. And this is some of the things that now we're starting to think about in terms of synthesis and HRI, for example, in terms of correct behavior is not enough. It has to be correct behavior that's perceived as correct behavior as well, right? So there's like a bunch of questions that we think about there. What could be the feedback here? The feedback here could be, I don't see a red block. Am I going to see one? Right? So we have some work on being able to use the information that we have from the task and from the grounding of the words, so blue block, red block, and all these things, to say, what, I can't do it in this current situation. So you asked me to pick up the red block. Am I going to see a red block? And then you can continue from there. All right, so that was a very quick going through. Really, the point of that was to show you that the questions of synthesis and feedback and abstractions are really capture a whole bunch of different robotic systems that we should care about. So these are some of the robots that we actually worked with in the lab using different, within the context of synthesis. We have some work with soft robots now. I don't actually have, this is on my desk, so it's a forklift. We have a project with Raymond who does forklifts and automating that. That is not an actual order picker on my desk. Swarm robots, which I'll talk about a little bit, and so on. So these are the different robots we played around with, which each system, each robot, each domain, each set of tasks that I care about will likely have a different abstraction, maybe different formalisms to capture the specifications, and so on. So there's a lot of questions there. And we're thinking about ways to generalize this to more systems. So another, of course, shameless plug. We wrote my group is definitely not the only group that does this at all. So there's a bunch of groups that work in a bunch in the controls community and the HSCC community, the hybrid systems community within robotics. This is kind of a survey that we wrote for annual reviews, 2018. And this has a lot of information about how we think about what are people doing in terms of abstractions, in terms of specifications, probabilistic systems, continuous representations, and so on. Okay. Okay, so this is the common theme. This is how I'm thinking about things. What are abstractions? What are specifications? What are synthesis algorithms? And what is feedback? Those are the questions I care about. And the more I think about this, the more I care about the feedback aspect of it. What can I say? What can the robot say to the person, or to the other robot, for that matter, in terms of what it can and cannot do? All right, so what I want to do now is I want to talk a little bit about the abstraction synthesis side in the context of swarm robots, and a little bit on the synthesis itself and how we need to change the synthesis algorithm to accommodate for physical robots or for physical environments that have some uncertainty in them. And I don't mean probabilistic. I'm not talking about distributions. I'm talking about the fact that a robot is moving around and some things might happen that I didn't expect. So that's what I'm planning on doing. I'll talk about the swarms. Hopefully I'll have time to talk about the other, and then I'll wrap up. So before then, let me make sure that nobody comes out of here without seeing linear temporal logic. So you should at least have seen it once in your life. I'm kidding. Okay, so what is linear temporal logic? So if the easiest way to think about this is if you think about propositional logic, which you've all, I'm sure, seen at some point in your life. I have A, B, they're either true or false. I can start talking about A and B, B and C, B not B, B and not B, and so on. Linear temporal logic adds temporal operators on that. So I can now, the truth value of propositions change with time. So an example is Hadas giving talk. That's a proposition. That proposition is currently true and will not be true, I promise, in 35 minutes. Okay? So that's the way you want to think about that. So now we can say a formula. Eventually, Hadas giving a talk. That's true because I'm doing it right now. Always Hadas giving a talk. No, thank you. Okay, that's definitely a no. So that's the linear temporal logic. Reactive synthesis, which is a process in which you can take an LTL formula and generate a controller from that, and we'll talk a little bit more about what I mean by controller, is the notion of, the notion of reactive synthesis allows you to take a formula and generate a design from that. So this is kind of a seminal paper by Pnueli and Rosno from '89. The idea there is you have propositions that are inputs and propositions that are outputs. Robotics speak, we have sensors, or we have perception information, and we have actions, or actuation, or control, right? The information I'm getting, I'm not controlling. That's the environment, they're doing their thing. I'm getting information from that. What I'm controlling is what my actions are, the robot's action. So X is input, Y is output. So now I can write specifications over this X and Y, and what I want to do is I want to generate a design that no matter what X does, no matter what my environment does, I have something to do to satisfy my specification. And that's the notion of reactive synthesis. It is a worst case approach. If the environment can do anything to make me fail, no synthesis. And there are things we'll get around with that. Okay, so in this example, we have not X implies not Y, and always X implies eventually Y, and always not Y implies not Y until X. So there are multiple different solutions to this specification. This is one of them. So if you squint at this a little bit, or we can chat about it later, really what you can see is that one possible solution is that just Y does what X does. So if X is false, Y is false. If X is true, Y is true. Done. There are other solutions as well. Synthesis of the full LTL, reactive synthesis of full LTL, is computationally terrible. Some people have developed tools, but anything that I do really doesn't scale to millions, but synthesis, it's double exponential in the size of the formula. It's not good, right? We don't like it. So actually it was a 2005 paper, 2003 paper maybe, that they came up with the original paper was Pnueli, Peterman, and Sal, and they came up with a fragment of LTL, so it's called the GR1 fragment, and that fragment restricts the form of specifications that you're allowed to use, but also the computation is much better. So it's polynomial in the state space. Still not great, but much better than double exponential. So this is the form of the formula. You have phi e, which is assumptions about x, assumptions about the environment, implies phi s, which is what I want the robot to do. Now, of course, there's more structure in there, right? So there are more constraints on what the structure is, because otherwise I could just write anything there. So we're going to keep that in mind, this implication, the fact that I'm assuming something about the environment, and if that holds, then I'm going to get desired robot behavior. All right, so that's the reactive synthesis. Why am I presenting that? A lot of my work has to do with reactive synthesis, although we've been branching into different types of synthesis, different specifications, and I'll talk very briefly about that at the end. So I want to talk about swarms, and I want to talk about swarms. When I talk about that, I want to talk about what the abstraction is. So swarm robots, we had a really nice discussion at lunch. I don't know if people are here. This is Mike Rubenstein's work with Radhika Nagpal when he was at Harvard. This is the kilobots. I'm sure you've seen this before. If not, you really should Google Mike Rubenstein and see the really cool things that they did. This is definitely a swarm. This is 1,024 robots that can create these shapes. And the control is very simple. Each robot has its own control law. And together you can see this emergent behavior. So this is kind of the definition of swarms. You have very simple behaviors, and I'm sure there are people in the audience who do this anyway. Very simple behaviors that, when composed as a collective, create this emergent behavior. So it's very, very much a bottom-up approach to designing these kind of. Someone designs. Let me stop this. Someone designs these specific rules and can analyze the overall behavior of the whole system mathematically, experimentally. There's a lot of really, really exciting work in that space. What we did was to look at the opposite kind of directionality. So what I want to do is I want to write a high-level specification for the swarm. And when I mean swarm, I mean I don't care about individual robots. I don't actually care how many there are. There could be 10, there could be 100. I want to write a specification for the whole swarm, and I want to automatically generate individual control laws for the different robots that satisfy that high-level behavior. So it's the opposite direction. So you have a specification, we're going to synthesize, we're going to get controllers. And the controllers are going to be continuous controllers. So it's going to be velocity commands, for example. So let me give you an example of kind of a simple scenario. These are sphere robots that unfortunately are all dead in my lab. They don't charge anymore, which is very frustrating. We put a cage on them for Vicon, so we're not doing any estimation of them. We're under a Vicon system. And they're going to be moving around. So the task here, we're given, this is the task. I don't even know how many robots I have. Every robot should go through C, the top. All robots should be in D, E, and F at some point. All robots should be in A and B at some point. And they can never be there can never be robots on both sides. Why is this my task? Because that's what I want. But it's an overall collective behavior that I'm specifying at the high level, and I need to generate these different behaviors. So I'm going to go over kind of the process in a second, but what you'll see is that behaviors like this. So they're red, blue, and green are the robots we are tasked. So we created 3 programs. You need 3 programs for this. We just randomly assign them to robot. The yellow one is driven by my student and is acting as a dynamic obstacle. So that one is just being in their way. So what you can see, the robot, we wrote a specification. We generated a controller, a continuous controller, that's guaranteed to not only satisfy my task, but also avoid collisions with a dynamic obstacle, assuming the dynamic obstacle is not faster, because then really nothing you can do. Nothing you can guarantee. So how does this work? We have a temporal logic specification, and I'll talk about, so when we have temporal logic, we have propositions. What are these propositions, right? These propositions should mean something for the swarm. So I'll get to that in a second. But I can write a specification over that. We generate a symbolic centralized controller. So you can think about that as a state machine. And then we discretize that, or we partition it into as many individual programs that we need. In this case, we needed robots to be in 3 regions at the same time, so we needed at least 3 programs. We automatically determine how many programs we need, and we create a synchronization schedule that synchronizes, that says when do different subswarm need to synchronize to make sure we're satisfying our task. And I'll get to that in a second. Okay. So this is, again, another very simple example. The task is you want to go, the whole swarm needs to be in A. Everybody needs to go through E. It doesn't have to be at the same time. So we can talk about kind of macro and micro behaviors, and we talk about that in the paper. Some of the robots have to go to B. Never can be in B and E at the same time, and never enter D. Now I have never entered D. Another thing I could do, I could basically remove it from my state space. Definitely could do that. But maybe I want to have that for a different task. So I could play around either at not allowing any robots to be there any time, or just putting it in the specification. We play around with both. Okay, so what are these building blocks? What are these propositions that we need? So we're gonna, when you think about single robot or multi-robot, you can assign a location proposition for each one of them. So I have 3 robots. In 4 regions, I could have 12 propositions, robot 1 and region 1. It's true if the robot is in region 1, false otherwise. Here, it's a swarm. I don't care how many I have. I don't want to deal with individuals. I don't care if some die along the way, to a point. So my specification, my abstraction now, is a proposition is going to be true if in that region there's at least 1 robot. So now there's no mutual exclusion. I could have all of them true at the same time, and so on. So I can think about building specifications over regions that have at least 1 robot in them. And then, from the task that I had before, I can create this symbolic behavior. So everybody starts in A, synchronizing there. Doesn't really matter. I'm not going to go into that. Everybody goes to B. Everybody goes to E. Everybody goes to C. This satisfies that task. Is it good? Should I just run this?
There's going to be sometimes robots in E and E.
Excellent. Excellent. So here, my symbolic abstraction says, OK, you're going to go from everybody in B to everybody in E. Great. Symbolically, that's totally fine. Physically, I cannot implement that. There's no way I can implement a whole swarm teleporting from one region to another. So really, the problem is that this transition is not physically implementable. And a lot of the work that we do in terms of synthesis, we kind of go back and forth between the symbolic and the physical. And we have to have guarantees in terms of simulations by simulations, doesn't really matter, that allow you to go from one space to another space, from the continuous to the discrete, from the discrete to the continuous. So in this case, the discrete is fine, the symbolic is fine. I cannot do this physically. Okay, so what we would do? We would create a different symbolic plan. And this is already distributed into 2 groups. Some of them will go from A to C to E to C to A. And some of them will go from A to C to E to C to B to A. Because only some of them need to go to B. Yeah?
So would your system give you feedback to allow you to come up with these plans?
Yes. So actually what we do here is we automatically change the plan to accommodate for the physical implementation. So I don't even, the user doesn't even have to be involved, because I look at that because I know that my abstraction does not actually allow me to teleport from one to the other, so I can already remove that in the synthesis algorithm. Yes?
I guess this slide's fine. So if you have that never occupy B and E at the same time, so I recognize you can't have the swarm go from B to E, that's impossible. We can't have a collection of I don't know what you call the collection of specifications, come up with a set of policies that would just prevent the swarm ever being in B and E?
But then it doesn't satisfy all robots repeatedly visit E, and some of the robot has to visit B.
Oh, okay, so it contradicts them.
Yes,
okay.
yes.
So then would your thing come up with a conclusion that says not possible?
But it is possible. I just need to change my controller. So if I keep going through C, there's no problem. So what I'm assuming, I should actually clarify. What I'm assuming is that I can, a transition between 2 regions, I cannot do that instantaneously, but I am going to assume that the swarm is either in one region, in the transition, or in the second region.
So I think it's not
Yeah.
possible, but on the previous slide, you had this graph of this goes to that, and this goes to that, and so forth. With that graph representation, can your synthesis say this is impossible?
Yes, it does. So it does, because that's why it changes it to figure out that it really should do this. Or any, I mean, there are multiple solutions for this. This is a solution for that. Yeah. So yes, this happens automatically. But what you'll see here is that even this is not quite enough, right? Because now if I have two subswarms, and each one of them is doing their own thing, now if one is going from A to C to E to C, and the other one back to A, and the other one is going from A to C to E to C to B and back to A, depending on how fast the relative swarms are, and I'm not assuming anything about them being homogeneous, same velocities, square environment, I'm not making any of these assumptions. There is a timing between them that could cause them to still fail, right? So if the top one is just ridiculously slow, they're still stuck in E, and the other subswarm is ridiculously fast, and they already made it to B, I'm violating my specification, right? So what we do, we automatically generate these synchronization points. So that's the stars that you see here. Synchronization points in which the subswarm have to say, okay, I'm at this point right now. And only then they can continue. And that guarantees that I'm not violating any of my safeties. I will note that this is only a problem when we talk about safety, right? So safety is things that should not happen or things that should always hold. Things that eventually have to happen, we don't really need those things. All right, so now we have the two different programs. Yeah?
The synchronization points also generated by the algorithm?
Yes. Yep. We automatically generate we are, now let me remember what we say. So we are guaranteed to get I think, we're not guaranteed, I don't think we can guarantee, we cannot prove that we will always get the minimal number of synchronizations because the way we're doing it. But under some constraints, we are getting kind of, we're definitely trying to minimize the number of synchronization points. Yeah. So what we got here, two programs for the two subswarms. Now I'm going to assign some of the robots one program, some of the robots the other programs, and let them run, assuming while synchronizing those points. Now this is a discrete thing, right? So the video I showed you is robots moving around the workspace, right? I want a continuous control behavior. So what we do is we kind of leverage some of the work on control barrier functions, and we create controllers that are guaranteed to satisfy the discrete transitions. So it's not enough for me to say go from B to E. You need to, or not from B to E, from B to C. You have to go, or what do I have here? From A to C. For me to correctly implement a discrete transition between A and C, I have to guarantee that the robot actually goes from A to C, so there's a liveness or reachability aspect of it. But I also have to guarantee it's not going through anywhere else, because if it's going through anywhere else, I'm violating my discrete plan. So the way we do that is we kind of create virtual walls around the boundary of those two, over the boundary of the union of the two regions. And then we create control barrier functions or we create kind of a nominal controller, and it has control barrier functions that kind of bump it away from these virtual walls. So we guarantee safety. So these control barrier functions guarantee safety, also guarantee safety with respect to the walls. So it's never gonna go to a different region. Also guarantee safety with respect to other robots. So never gonna collide. However, they don't guarantee deadlock. So it could be that you have a lot of robots and a very narrow passage, and they're just not going to work out. So we have some ideas of how to deal with that, but we cannot guarantee. Question?
What happens if there's a perturbation and the robot is pushed to region B?
Great. The question was if there's a perturbation and a robot gets pushed out to region B, typically it would fail. So there's not a lot. Typically it would fail.
So
that's true.
Can I ask a two-part question?
Yeah.
So the first thing is are you considering dynamics, like acceleration?
No. In this case, no. We're kind of using based on kind of stuff that Magnus Sagerstadt with the control barrier functions. So it's a kinematic model.
Okay. So what about velocity?
Sorry.
What about velocity?
Velocity. So we're controlling velocities.
There is.
We're controlling velocities.
Okay. I meant to say velocity, not acceleration.
Okay.
So then I would imagine if you have a bigger domain now, there's the opportunity for those agents to go faster than they would have done with the individual domains. In other words, when A goes to C, you only have a certain guarantees to how fast the agent can go with A's policy, and then likewise with C's policy. But now it's a bigger domain. There's an opportunity for the robot to go faster. Do you exploit any of that, or am I just making stuff up?
Do you mean like having multiple transitions, go through multiple transitions?
Now you don't have a transition.
I do. The transition is the shared boundary.
Oh, so you still say there's a transition there?
There's a symbolic transition there, right? From where I'm going, when the subswarm is going from A to C, it's going to be an A, then it's going to be an A and C together, and then it's going to be in C, and that completes the symbolic transition.
Right, so if you treat it as one big AC, and
Yeah.
I think when we talk to you later, now I think there's an opportunity for you to go faster with the agent, because before, when you went from A to C, there's only so much time for A to, you can't speed up, this is no acceleration. All right,
We treat this as one region with kind of an area that we want to reach within the next region. So we are treating it as we don't, at the physical level, we have this one region we're trying to get from whatever initial condition we are to the kind of goal region. Yeah. It was not a stupid question. Okay, so that's a little bit about the swarms and how we think about abstractions for swarms. Yes?
So following up on the deadlock aspect of
Mm-hmm.
something, is deadlock introduced just because of the short look ahead of the control barrier functions, or without the barrier functions also there is a possibility of deadlock?
The reason for deadlock is if you're trying to maintain a safe distance between robots and you have kind of a narrow passageway, it might just, imagine you walking down the hallway and there's another person in front of you and you want to maintain this personal space. It's going to deadlock, right? Unless you coordinate, and there's no coordination here, right? Each one has their own, so it has to do with the safety controllers. So it is with the control barrier functions. So if I don't care about colliding with anything, I wouldn't get deadlock. But my preference is safety in this case. Okay, so yeah. No.
Let's talk about the sense of optimality here. Like once you have a design that comes out, can we get into optimality on the front end?
So define optimality in this case.
In this case, would be like the fastest way to get around.
Oh, okay, so you're talking about fastest way implies something continuous. So we have some discrete abstraction. So what we're going to get a minimal number of transitions, which does not necessarily correspond to the fastest, right? It also depends on how long it takes, especially when you have a bunch of them and you're trying to go through a narrow area, they're kind of like, right? So we don't have guarantees on that. But we do have, the way the synthesis algorithm works, it will give you the minimal number of transitions.
But there is no sense of a cost function.
No, there's no sense of cost function. Yeah?
Are the controllers of the individual robots formally verified, or is that just assumption?
So it's, so the question was, are the individual controls formally verified? So control barrier functions do come with guarantees of collision avoidance. So they do have guarantees. They are verified, or they're correct by construction, if you will. But I will say with respect to the model of the system, which is x dot equals v, or whatever it is here, right? So whether that model is a good model for the physical system, that's a different question. So verified with respect to the model, yes. Verified with respect to reality, for the spheros, yes. For a tank, no. So that's kind of the way we want to think about that. Okay, I think I have enough time to kind of maybe go quickly through. So that was a little bit about the swarms, to give you a feel for a system. What are the abstractions? What are the synthesis algorithms? Where do the connections between the symbolic and the physical, and how do we think about that? Going back, so this now I want to talk a little bit about in terms of the synthesis algorithm itself. So the synthesis algorithm, not developed by us, developed by people we collaborated with before we collaborated with them, takes an LTL specification. We collaborated with them after. That's because, anyway, yeah. I have a paper with Neil. So Neil Peterman, we have a paper on timing semantics. It's actually a cool paper, if I may say so myself. So the synthesis algorithm takes in an LTL formula of this form, phi implies phi s, spits out either can't do it, or here's a state machine that's guaranteed such that every execution satisfies my LTL specification. But this is an implication. So this formula is true if what? If the right-hand side is true, or left is false, thank you, okay? If the left is false. So really baked into this algorithm are the assumptions about the environment. So I'm gonna go from here to Howie's office. I'm gonna assume the door is open. Assuming this door is open, here's what I'm gonna do. I go to the door is closed. My assumptions failed, and the environment failed me. This is on you, not on me. I'm just gonna hang out here, right? This is I am satisfying my task. And this is a worst case approach. So what happens when it doesn't hold? Okay, so that's the question. How do we robustify the system to assumption violations? So this is, let me give you kind of a context of a paper that Catherine Wong, who was a PhD student with me, did a while ago. So we have a robot, the task is fairly simple. This is part of the specification on the top. Left-hand side, actually let me start with the right-hand side. The right-hand side is I want to go to the corridor. I'm going to start in the mailroom, I want to go to the corridor. Very simple. My safety specification is if there's a door, if the door is closed, I cannot go to the region marked door. Okay? Don't crash into the door, basically. That's a safety. So there's a door that can show up where it says door. Now I'm assuming, this is my assumption, the left-hand side, light blue, that if I'm in the hallway, the next time step, the door is going to be open. Okay, not next, door closed. So if I'm in the hallway, I know the door, I'm assuming the door is going to be open. So this is what you get. So we have a robot. This is the state machine that we get generated. We have a few more specifications, but this is what we get. We're starting in the mailroom. We're slowing this down a little bit. Don't remember why we slowed it down, but there was a reason. That's cat's legs. Mailroom, it's going into hallway. Suddenly the door is closed. We don't have a transition. Okay, it detects that the door is closed. There's no transition. You violated my assumptions. I am no longer obligated to the specification. Done. Okay? Which is not what we want. We don't want that to happen with robotics. We want to be able to be robust to some assumption violations. So what we did, we kind of looked at it in two different ways. First of all, we changed the synthesis algorithm to be more robust to environment violations. So now, when we synthesize, we also add transitions that violate environment assumptions, as long as those environment assumptions don't cause me to violate my safety, and as long as if at some point that violation goes away, I'm still able to complete my task. Okay, so what would that look like? Really what we automatically synthesize the previous controller plus 2 added transitions of what happens if the door is closed, even though you told me it's not going to happen. Right? You told me the door is not going to be closed in the hallway. But I don't trust you, and even if it is closed, here's what I can do. Now notice that if it's closed forever, I cannot complete my task, and I won't know about that. So I'm assuming it's a transient violation. So then what you would get is something that looks like this. It's going to be executing those, and then it stays in, it's in another state and goes and continues in its own merry way, which is good. The other thing we did was say, where are these assumptions coming from, right? I might not put any assumptions on my behavior, which is fine. It might mean that I'm not able to synthesize, because remember, this is a worst case approach. So if the environment can do, if there's any behavior any sensor information I can get that will make me fail, can't synthesize. So maybe I'm making some assumptions. But those assumptions might not be good, right? I just made them up. So what we want to do is, as we're running, I'm laughing because I'll tell you in a second. We're going to characterize the environment and automatically rewrite the specification, the assumption side, to weaken my assumption about the specification, the assumption about the environment, and then continue. So when we wrote this paper, we were very deliberate in not ever using the word learning, because we are not learning anything. The only thing that we're doing, if I think about learning, and people here should correct me if I'm wrong, when I think about learning is I have a big space of models, and I'm using data to narrow that down. Here what we're doing is we have a strict assumption about the environment. I'm trying to relax them. You know what, then you told me the environment can do this, but oh no, I see it also doing this. So let me weaken my assumption. And if I can still synthesize, great. If not, you'll see in a second. So this is the example there. This is what happens. So what we're doing is we're basically saying, you told me the door is closed, but now I see the door is open. Okay, so the door can also be open. So now the door is open. So I don't see the door is still open. I'm adding, or the door can be open. And now I'm going to add, sorry, this takes for a second. Now I'm going to add, oh, you know what? Now I see the door is closed. So the door can also be closed, right? So basically it turns out that my assumption is just true, because it could be either closed or open. Now in this case, there's nothing I can do to resolve. I cannot synthesize, because if the door is closed forever, I can't accomplish my task. So now I can go back to the user and say, you know what, here's my problem. If the door is closed forever, can't do this. Is there any assumption you can give me about liveness, about something that will eventually happen? So the user can say, you know what, don't worry, eventually it's going to be open. So if it's eventually going to be open, now we can continue to execute. Okay, so we're modifying the assumptions. We can change the safeties based on observed information, and we can ask for help if that assumptions are too, they're not enough assumptions to generate the task, and ask for, you know, what else can I assume from the user? What we could do this, what we did with this later on is this is a robot and an environment that it doesn't control. But a lot of these ideas also work for a multi-robot situation where there are two robots or multiple robots acting in an environment, and working in the same shared environment, but doing their own thing. So this is not a collaborative situation. It's fully decentralized. Everyone has their own specifications. But what we can do is by figuring out what assumptions are violated. Actually, let me not run that yet. Figuring out what assumptions are violated, I can automatically ask the other robot to take the assumptions I'm making about them and incorporate that into their specification. Very simple task. We have blue wants to go to the blue flag, orange wants to go to the orange flag. They're not allowed to be in the same region at the same time. Each robot is assuming the other one is going to be out of their way. They're running, what they see now, there's a conflict. The blue robot gives the orange robot information about what the blue robot is expecting. The orange robot says, you know what, okay, I can do that. Puts it in their own specification, resynthesizes, and continues, right? And this is fully automated. There is no human intervention at this point. You will notice that the orange robot is not doing the most logical thing, right? It's going all the way around instead of just stepping back. So no notion of optimality here. But it is fully resolved autonomously, and we have some solutions there. Okay, I promise you to end in 5 minutes. So again, this is the picture. This is the picture of my lovely daughter and my vision of my works, of my research vision and the things that we're working on. I want to talk a little bit about opportunities and future directions. So I talk a lot about guarantees. I want to get guaranteed behavior. You asked me about the verifiable, whether the continuous controllers are verifiable. Can I automatically change things? So yes, to a point, because we have sensors that fail, right? That make behaviors incorrect. We have hardware that fails. Love this. There's hardware that fails. We're not taking that into account. And there are people that fail. Okay, this is yeah, you guys probably have seen this before, but this is children getting in the way of a robot trying to do its thing, right? So, yeah, so everything can fail. So now the question is, can we really guarantee everything? And the answer is no, of course we can't. But we can increase the trustworthiness of a system, and we can provide feedback about when it can go wrong. So a lot of the questions, so I'm going to put a big red asterisk next to guarantees. And we want to talk about what are the assumptions we're making. Can we falsify? Under what conditions do I know the system will fail? Those are kind of questions we're playing around with now. Questions of abstractions and scalability are always interesting questions. Kind of, is there a general way to create abstractions? I'm skeptical, but maybe we can look at classes of systems and classes of tasks. That makes sense. And we can apply this to these ideas to many different domains. And I'm kind of really excited about, especially the HRI aspect of it. So this area of people I need to talk to a little bit more. So these are a few examples of very recent papers in collaborations with HRI researchers, where we're looking at different formalisms, different synthesis algorithms, different guarantees. So handover using a signal temporal logic encoding. It has some continuous values. Kind of side-by-side walking with an SMT encoding, satisfiability modular theories, and just recently accepted into HRI, LTN encoding in the context of clinicians generating behaviors for robots. All right, so I promised I will be on time, and I am on time. So this is a lot of acknowledgements to a bunch of students over the years. The earlier it is, the longer my hair is. So you can kind of follow that. And this is kind of older. I need to get a new group picture. But I just want to leave you with this vision. And thank you very much for your attention.
Okay, so I know Howie has to disappear because you have a 4:30.
Hey, Jody told me she's going
Okay. And I'm supposed to be somewhere at 4:30. So what I'm going to let happen, and I'm going to let Howie, because he can stay late, start handling the Q&A.
I can handle the Q&A.
And if Howie has to leave, Sonia will stay. So who wants the first question?
Well, this is going to be easy. I'm going to give everybody.
Okay.
All right, first question. Nobody has a question?
Nobody has a question. It was.
Sonia will ask the question. Okay.
Don't-
I will be
I told
back.
you I would ask questions.
Please. Yeah. So thanks, Aaron.
So you motivated this with beautiful videos of DRC and autonomous cars and all this stuff. So what is, this is a very high level question, where's the biggest gap in all of these pieces in your diagram? Which parts maybe present the biggest challenges, or do they all present challenges? Or what do how do we get from here to self-driving cars or to HRI, like real
Yeah.
HRI systems that are deployable?
So I don't know if the people in the back heard the question, but the question is, what is the gap that allows this vision to actually materialize into fielded systems? Fair? I think there are multiple. So one of them is a lot of these techniques assume we don't really have good ways to think about how to deal with perception, and more specifically uncertainty that comes from perception, right? All of these things I assume I know my state. If I don't know my state, what can I still maintain, right? So those are kind of questions that come up, especially in the self-driving car domain, and people are using, as far as I know, they don't really like to talk about it, but some of these techniques of synthesis and formal methods are used in the self-driving car domain. So I think Newtonomy or whatever, whoever bought them, I don't remember, have used some of these techniques at least. So questions like that are, the gap between actual physical world through perception and the fact that we're assuming state information, perfect knowledge of state. That's a big gap. The other big gap is what abstractions to use for a system, right? So we've done a little bit of synthesis for the DRC with the atlas that we had. Actually was Dave Connor was the PI on that, Howie's former student. And you have, so also we started came in late. So there was a full a full ROS stack with a whole bunch of messiness, and thinking about that in kind of nice breakable pieces and how to compose them is difficult. So we were able to do some things, but it's not a fieldable thing. Yeah, those I think, and those are the two main gaps I think that I see. I will say that maybe this will come up, but I want to kind of address the question of learning. Where does learning come into play here? And I have a pretty strong opinion about where people should employ learning. So creating the abstractions is a perfect place to use learning in my mind. The only thing that I will say that when we create those abstractions, I want to have some guarantees or some understanding of what these pieces can do. And when they fail. Because it's fine that they fail. I just need to understand when, so I can be careful with how I compose them. So those are places where I think learning comes into play really, really nicely. Yeah, maybe assumption, maybe kind of articulating assumptions. So one of the things I like about synthesis is that whenever we build a system, in general, we are making some implicit assumptions. Everybody makes assumptions in the way you design things and the way you expect where it's going to be. And in these kind of synthesis approaches, you are explicit about the assumptions you're making. And then you can reason about it, you can monitor whether these assumptions are holding or not. So the questions are what the assumptions are for these abstractions, for maybe from the learning, and those are kind of really interesting questions that I'm happy to collaborate with. Jessica.
So following up on how you select those abstractions or learn those abstractions, I was interested in how that plays into your system diagram before we have feedback to a user to refine their definition of the problem. And I'm interested in how abstraction plays into that, because it might be that your current formalism needs to be changed to a different level of abstraction, but the model doesn't know what's available to it. So how do you think that plays into how your system would request an abstraction or even detect whether it needs that?
Yeah, so that's why the arrow to the, I'll get there in a second. The arrow to the abstraction is the lightest, because that is a hard question, right? So there's Okay, let me actually answer from the easiest part, right? So if I have a dynamical system, and I have some abstraction that takes pieces in the state space and says, okay, this is my continuous dynamics, these are the pieces in my state space, and these are my transition relations, this non-deterministic transition relation that I can create from the dynamics. And there are people who do that. There's there are tools out there. A bunch of people are doing that. And now I can see by trying to synthesize over this non-deterministic abstraction whether I can actually guarantee anything. And if I can't, I can go and automatically refine my abstraction, break down these state spaces into smaller pieces. Of course, they're going to be computationally more expensive, but I can do that. So that's very simple because I talk about a dynamical system with a very understood state space and all that. How I would go about saying, okay, this abstraction is not quite the right one for me for like more general. I'm not quite sure, right? That's an excellent question. That's a research question that we have to figure out in terms of this feedback. But the easiest thing to say is to say, you know what, I have a building block for opening the door, but to get to the door I need to push it, and I don't have anything to do that. A little bit like the modular robots. Then I can tell the user. Maybe I can then even use, a paper we just got accepted into ICRA looks at, let's say I have a bunch of skills. Someone gave me a bunch of skills. I learned a representation for initial condition, post condition. I can compose them. Now I want to write a specification over this whole thing. I write a specification, it's unrealizable. Now I can go back and find which skill I'm missing. It doesn't really matter what the details are, but I can find, what I can tell you now is you know what, if you had a skill that will take me from this state of the world to this state of the world, now I can do the full task. So that kind of, it's starting to get to the question of where are those missing blocks. The level of granularity is a much harder question, but missing pieces is something that I can do. Yeah?
You mentioned that there's no sense of optimality with the paths that are generated.
Continuous optimality.
Sure, right. So I'm curious because I'm assuming there's multiple satisfying assignments for a model. So could you maybe look at enumerating different satisfying models and then trying to come up with some idea of shortest paths there, or adding in extra constraints that say, oh, I want some low cardinality on the number of steps I need to take? Are there ways we get it?
Yeah, so we actually had some work on that. I didn't present it here. It was not in the context of swarms. But what we did, so first of all, it will give you the minimal number of transitions, which doesn't necessarily correspond to physical shortest path. So what we did is we created this kind of cost tuple, because in the reactive synthesis, there are two things. There's kind of the continuous cost for executing a transition, but also if you're waiting for the environment to do something, that's another cost, right? So I can say I want to go through this door, and the door is closed, and I just need to wait for it to open. So I might wait forever at that door. Well, not forever. I will wait a very long time, but it would be shortest distance, as opposed to me going through all the way around, which won't cost me almost any time, but a lot more energy on the path, right? So we defined this kind of cost tuple that allows you to prioritize, to create this partial order, to say which you prefer. And we're able to, yes, you're right, there are multiple solutions, and we're able to prioritize based on that. So we have some work on that, but again, it's mainly in the single robot. We didn't extend it to the swarm stuff.
Cool.
Mm-hmm. Yeah.
So this is going back to the question about how can you learn assumptions at the right level of granularity. And formal synthesis methods work really well when there's complex in specification, but then as you work in the real world, you may start seeing more complex, but then they may not be very common. So at some point, maybe actually to not think about that and just reason at a much higher level, but then they can come up. So have you looked at works or found works that navigate this trade-off very well, where you can have very detailed specifications that hold true of every kind, but then you don't want to always work at the very fine level, so you want to a little bit high level, but sometimes they don't hold. So making that trade-off very simple is really hard.
I don't know if I would call this different level of granularity. I think what you're saying is, how strict do I want to be about the assumptions holding, right? So then you can start talking about probabilistic systems. So there are probabilistic logics, there's synthesis over probabilistic systems, MDPs. I don't think I've seen a lot of POMDP work, but definitely MDPs, Markov decision processes, that look at, maybe I'm not, so the reactive synthesis I talked about is worst case. Maybe I don't care about worst case because really, I don't, if a meteor falls on me, it's going to follow me and kill me, I don't care, right? So that's kind of the mentality. So then you can start talking about probabilistic representations. Some of the continuous metrics, some of the continuous logic, so single temporal logic, for example, has this really nice notion of robustness. So you can say, how far am I away from violating my specification? So it's not quite a reactive. There is some work on reactive. It's slightly a different expressive power, but you bring. I think what you're bringing up is the fact that the worst case is not really realistic for robotics, and I 100% agree with that. So then the question is, how do you robustify it, either by assuming it's transient, or move to different representations that allow for that kind of uncertainty or kind of average case as opposed to worst case. Yeah. Yeah. Say again?
The role of noise or statements.
Yeah. So we're starting to look at it now. So there has been work in the past on actuation uncertainty. So I want to move from Cullen Belta's work. So specifically Morteza Lahijanian, who's now at Boulder, has done a bunch of really nice work there. I want to move right, but actually my action, instead of moving right, I move forward, right? So that's actuation uncertainty, but I'm still assuming I know my state. Not knowing my state is something that we're starting to figure out even how to reason about, because what does it mean to the robot moving around only has whatever estimated state they have. So what does it mean to violate the specification when you don't even know that you're violating it, right? So you can think about some probabilistic representations, you can think about belief spaces, there's a bunch of, but that is a kind of a current area of research that people are looking into, especially in connection with perception, especially closing the loop with perception or with deep learning and all that as for perception. Those are really, I don't have a good answer for that, but it's a really exciting direction.
So maybe we have time for one last question, and then we're going to wrap up just for the sake of time and start moving this over to the reception.
Yeah.
So
yeah.
Pick one more.
In the first piece of work that you mentioned where you were using Sketch, you hinted that in hindsight, maybe program synthesis wasn't the best option after all. Could you please elaborate on this?
This is recorded and you're going to get me in trouble with Armando. So just so you know, Armando Solar Lizama is a professor at MIT who built the Sketch system, which is a program synthesis technique. So really at its core, it's a nonlinear optimizer, right? So it has this kind of, it combines kind of SAT or you know this, but I'm kind of explaining. It combines symbolic solver, so a SAT solver that kind of talks about this symbolic structure of the problem, and then a nonlinear optimizer that kind of finds solutions for that. In this case, there wasn't enough discrete structure to make sense of using Sketch. So it wasn't, and we had to kind of reformulate it because it didn't. So for forward and inverse kinematics, you need sines and cosines. Sketch does not like sines and cosines, so we had to reformulate the inverse kinematics. So now what my student is doing, she moved just basically to using FMinCon, right? So using a MATLAB nonlinear optimizer and being smart about how she's encoding it in a way that will get a solution. I love Sketch. So the program synthesis work is really amazing. Armando's a collaborator, but didn't fit this much. We realized it doesn't fit quite well with this.
All right, please.
On that happy note.
Thank Hadas, and we'll head over to